Okay, today's lesson, there's no math, which is hopefully good. It's all theory in terms of this concept, okay? So I mentioned to you guys last day that Isaac Newton is probably one of the most influential physicists probably ever. He came up with 3 different laws of motion and wrote them in a book. And so for the next 3 days, we're going to talk about each of his 3 laws. Okay. So here's his first law. When viewed in an inertial reference frame, an object either remains at rest or continues to move at a constant velocity unless acted upon by an external force. What?
So like if you throw something up, keep going, and something else stops it.
Okay, I'm going to give you guys a lot of different examples here. If you've even looked through the notes at all, what I've got is a lot of pictures of everyday life scenarios. And I'd like to try to use those pictures to relate how Newton's first law works. Okay, so I'll come back to this slide in a bit. Let me give you an example of a picture here. You're driving on an icy road. Okay. Hopefully you've never been here before. I have. It's absolutely terrifying. When you're driving on the highway, you're going 100 kilometers an hour, it gets slick, and you need to stop. You step on the brakes, and you don't stop. Anyone been there before? It's absolutely terrifying. We got in an accident Thanksgiving weekend 5 years ago where we did donuts in the middle of the highway, and I'm so thankful there were no cars oncoming because the car was not stopping. Now here's how this has to do with Newton's first law. Unless acted on by an external force, objects in motion will stay in motion. When you're trying to stop your car, what force are you hoping will take effect? Friction. Yeah, you want the brakes, the frictional force to take effect. But what happens if you're driving on pure ice? Well, really there's not a lot of friction anymore, right? So what happens is your car is going to keep going until some other external force stops you. Like a tree, or the ditch, or please not be, but oncoming traffic. Does that make sense? So this would be an example of Newton's first law.
That won't really stop you, it'll just put you in another direction.
Well, it could stop you. I mean, if you hit something head on, that is a force that's completely opposing you. So let me just go back to Newton's first law again here. Read it. By the way, the inertial reference frame, really that just means, how do I want to phrase that? When viewing in a non-moving reference frame, like if you're an observer standing to the outside watching this happen, I think that's kind of what he's going for here. Okay? An object either remains at rest or continues to move at a constant velocity unless there's an external force. Does that make sense, the example on ice then?
What about that right there?
Oh, okay. Have you guys ever seen the magic trick? Where
Yeah.
not magic trick, you pull the tablecloth out,
Yeah.
right? Well, what's really happening here is these guys right here, these objects here, they were stationary. Right? What forces were acting on them? Gravity was acting down, and a normal force was pushing back up. Well, if you pull the tablecloth out directly this way right here, in theory what should happen is there's no forces changing the up or down directions. And so then the objects on the table should stay there as you pull the tablecloth out. Does that make sense? In theory, that's what should happen if you do it well enough. There's some other issues with friction, but so long as you do it fast enough and with limited friction, that's how the trick works. Does that make sense? Well, here's another picture then. You've probably been here at some point in your life. You're trying to get your car going and it's stuck in a ditch. So Newton's first law, an object will either stay in motion, if in motion, or if it's at rest, it will stay at rest. Well, here you've got this car that is at rest. You are trying to apply some force to it. Don't get me wrong. I mean, obviously you are trying to push your car out, but there's probably a lot of friction, and the issue with your car being stuck in the snow is there's too much friction for you to actually overcome. So if you can't overcome that friction force, will the car actually move? So Newton's first law could work for an object that's already moving. An object that's already moving will either not slow down, or an object that's not moving, in theory, would not actually move. Does that make sense? I've got another picture here. Another way that we sometimes phrase Newton's first law is like this. If the sum of all of your net forces is nothing, then your velocity will not change. Does that make sense? So like if I'm trying to pull this way right here, and they're trying to pull this way right here, are there actually forces acting? Sure, yes. But if the sum of the forces, if it's zero, right, like if they balance each other out, will these two guys, will they move at all? You'd say, no, there should be no change in your motion. Does that concept make sense? Okay, another picture here. I'm not that knowledgeable about rugby, but this is a scrum. Is that correct? Okay. Maybe you've been in this scenario before, because I know some of you guys do rugby, right? Okay. Let's say that there's like 8 people pushing in both directions. Let's say the forces on both sides are equal. In theory then, as you're pushing each other, will anybody really move? And you probably might say, well, no, that might not happen. But what happens if one team got going and then the other team tried pushing backwards with equal force? You might have experienced this before, because I know it happens in other sports like hockey and football. If you can get going and the other team tries pushing back, you can actually keep the scrum moving forward because you already had a velocity going. Does that concept make sense? Some of you are nodding here. Right? And so the physics behind it is, yes, these guys are pushing back equally hard as these guys. But if this team was already moving forward, it doesn't matter that this team is pushing back. You're going to keep moving forward slightly and slowly. Does that make sense? Kind of like the car on ice. The car is going to keep moving forward. It already had a velocity, so it's going to keep its velocity moving forward. Does that make sense? Another example here. Sometimes Newton's first law is used to describe lazy people. An object in rest will stay at rest. So someone lazily sleeping in a hammock, unless they have incentive to get out of said hammock, will stay there. So, does that make sense? Okay, an example that really applies to my life. We have 2 young daughters. This is super important when you've got little kids. You need to put them into properly strapped in seats. Why? Okay, so I mean, hypothetically, worst case scenario, we get into an accident. Kinsey ends in the back seat. Okay. What's going to happen in any sort of accident is your velocity as a person in the car is going forward, right? The car itself is going to stop suddenly in a crash. What happens to a person then is they try to keep going, and maybe you've seen pictures before. People can actually like go flying out of the windshields. You know, like that's why we need seatbelts. That's why we need airbags, because the person's velocity is still going forward. The car stops, that person is still going to keep going forward unless some sort of external force stops them. Right? So, I mean, airbags, car seats, seat belts are all necessary so that you don't fly out your windshield if you crash. Does that make sense? Slightly different example. Sports is a good one. Do you guys know hammer throw? Seen this before? Long story short, you spin this big thing around in a circle, and then you let go, and in theory you want to have it fly as far as you can. Whoever throws it the furthest is the winner. Does that make sense? Okay. I want to just draw a bit of a diagram here. We're actually going to do a unit on circular motion later, but as a person, okay, imagine the person is spinning this thing around in a circle. Is there a force on this object as you go around in the circle? The answer is yes, there's tension. Because the actual rope or chain or whatever it is there, that's a force. There's tension in the rope. Does that make sense? And we'll learn this later, but the way that works is that the force is actually you kind of pulling in as you go around in a circle. We haven't covered this yet, so it's okay if that doesn't really make sense, but technically there is a force. The force is of you kind of holding the rope as it goes around the circle. What happens if you let go? Well, that force is now broken, right? So you're no longer holding on to the rope, giving it tension, and so therefore if you let go, all of a sudden it goes flying off in another direction. Well, that's Newton's first law. An object will stay in the path it was going to unless an external force acts on it. In this example here, It's actually more like the external force stops acting on it, and therefore it can then take off. Does that make sense? Like you were applying a force in a circle. As soon as you let go, the force is no longer being acted on it, and now it's going to have a velocity going a different direction. That answers your question? Okay. Another example. People who carry trailers behind them have a couple of different things to worry about. I picked this one on purpose, horse trailers. Any of you guys have horse trailers? You're gonna drive quite slowly when you've got horses in a horse trailer. Like you can't slam on the brakes because you don't want your horse to, like crash into the front of your trailer, right? Does that make sense? Other issues people who drive trailers have to worry about is going down hills. Sometimes large trucks actually have to have like a barrier, like a steel barrier between them here, because what could happen is if you're going down the hill, the back part of your car might actually like try to get going a little faster than your vehicle itself and could actually like, come and crush you, if that makes sense. So like large trucks that carry like logs and steel and stuff like that, they have to be quite careful when going down hills that they don't get into like accidents with themselves. Does that make sense? So same issue here. If an object is in motion, I mean, if you were to slam on the brakes here as this truck driver, I mean, not only would the horse go flying through here, but in theory, if your trailer was heavy enough, your trailer could try to keep going. And I mean, this trailer here is really only being attached by a pretty small hitch. You know? Okay, that's a good point, right? But I mean, again, that's a consideration that all big trucks would need to take into effect, right? Like, you want to make sure that you can actually try to slow this trailer down. I don't envision this one does, though. It doesn't look like it would. What was that? Do you think this trailer here would have brakes on the back here? Oh, okay. I don't know. I'm not familiar enough with how that would work, but I don't know. Like just like a basic hitch, like. Okay. I'm thinking like I don't know much about a horse trailer, but like I know like my parents when we take like a boat out to the lake, it's just the ball on the end and that's all you're hooking up to the hitch. Maybe a couple of chains to make sure you don't lose it. So like in theory, like your boat or horse or whatever could come crashing into you if you slam on the brakes quickly. So, but yeah, brakes would help obviously. Does that make sense, the concept? Okay, one last thing. We're gonna watch a video.
Right now?
We're gonna watch a video.
Oh, yeah.
We're gonna watch the Magic School Bus.
I'm ready.
You ready for this? Okay. So I like watching Magic School Bus with my daughter because she's 2. There's one episode in the Magic School Bus. You guys have all seen the show at some point in your life? Yeah. Okay. There's one episode where they play baseball, and they try to play baseball on a frictionless surface. And I'd like to watch this video to try to illustrate some of the points about how Newton's first law works. Because as soon as the guy throws the ball forward, he actually goes backwards because there's no friction to keep him from going backwards. Does that make sense at all? You know, and as they like run into things, they bounce off them exactly. So the point I want to make is, again, Newton's first law is an object will either stay in motion unless a force acts on it, or it will not even begin to start motion unless there's a force acting on it. Okay. So we're gonna watch the Magic School Bus video. Just so you know,